Hello, welcome to 4.3, locating real zeros of polynomials. So in this section, we're going to try to find the zeros of the polynomials. Last section, we're kind of testing them. Now we're going to learn skills to find them, or develop skills. If f of x, the rational zeros theorem, if f of x equals a sub n x to the n power, plus a sub n minus 1 x to the n minus 1 power, plus dot dot dot, it's a polynomial with integer coefficients. So that's key. Integer coefficients, that's positive or negative whole numbers. Then any rational zero of f must be of the form p over q, where p is a factor of the constant term, your a sub 0, and q is a factor of your leading term, your a sub n. Okay, let's look at example 1. It says list all of the potential rational zeros of the following polynomial. Then use polynomial division and the quadratic formula to identify the actual zeros. So we're going to find potential zeros first. So our possible p's are going to be plus or minus 1. 1's a factor of 30. Plus or minus 2. Plus or minus 3. Plus or minus 5. Plus or minus 6. Plus or minus 10. Plus or minus 15. And plus or minus 30. The q is the factors of 2 would be plus or minus 1, plus or minus 2. So when we look at our p over q's, we're looking at, it could be plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 2 over 1, plus or minus 2 over 2, plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 5 over 1, plus or minus 5 over 2, plus or minus 6 over 1, plus or minus 6 over 2, plus or minus 10 over 1, plus or minus 10 over 2, comma, plus or minus 15 over 1, plus or minus 15 over 2, and then plus or minus 30 over 1, plus or minus 30 over 2. Now the list looks very long, but it will get smaller because, for example, 2 over 2 is just 1. So there's some fractions we're going to see come out here. So the p over q list would be plus or minus 1, plus or minus 1 half, plus or minus 2, plus or minus 3, plus or minus 3 halves, plus or minus 5, plus or minus 5 halves, plus or minus 6, 6 halves is just 3, plus or minus 10, 10 halves is just 5, plus or minus 15, plus or minus 15 halves, plus or minus 30, and 30 halves is just 15. So it is still a long list. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times 2, 26 possible zeros. But the key to this is that our zeros, if they're going to be rational zeros, they're going to be in this list. That's it. We could go through every single one until we found them. So sometimes you just have to start somewhere. And let's start with 2. I probably wouldn't start with 30 because 30 is kind of big. But start with something like 2. We have negative 2, 11, 1, and negative 30. That's going to be negative 2. 2 times negative 2 is negative 4. 11 and negative 4 is 7. 2 times 7 is 14. 1 and 14 is 15. 2 times 15 is 30. Negative 30 and 30 is 0. So I do recommend starting towards the middle part. You could have tried 1, could have tried 2. What this leaves us with is negative 2x squared plus 7x plus 15 times x minus 2. So here is this factor down a little bit. We're going to try to factor this next part down. So let's try, how about 5 out of this result? The negative 2, the 7, and the 15. Negative 2, 5 times negative 2 is negative 10, negative 3, negative 15, and then 0. So we have negative 2x minus 3. Which means this factors down to be x minus 2 times x minus 5 times negative 2x minus 3. So our zeros are going to be x equals 2, 5, and negative 2x minus 3 equals 0, negative 2x equals 3, x equals negative 3 halves. Those are the zeros. And those are among the list of potentials. So there are 23 we wouldn't have found. I mean, it would have been nothing, but those are the real ones. But now we're going to learn ways to minimize what we're going to search for. We don't have to look at every number. We have tools that we are going to develop that allow us to say, okay, I'm going to stop after that. I'm not going to check those, because if it didn't work to this point, it's not going to work down the road. So we're going to see that. We're going to be able to say, oh, we're going to have so many positives, so many negatives, or potential positives and negatives. It just helps us to find them. So let us continue. Descartes' rule of signs. Let f of x equals a sub n x to the n. Okay, we still have a polynomial here with real coefficients. Now this is real. It doesn't have to be integer. In the previous case, if they're integer, this is the situation. In this case, now we're just talking about real, any real numbers. And assume that a sub 0 is not 0. That your constant's not 0. A variation in sign of f is a change in the sign of one coefficient of f to the next, either from positive to negative or vice versa. The number of positive real zeros of f is either the number of variations in sign of f or is less than this number by a positive integer. So that means if it goes positive, positive, negative, positive, that's 3 possible positives or 1. You go down by 2 every time. The number of negative real zeros of f is either the number of variations in the sign of f of negative x, you have to evaluate that, or is less than this by a positive even integer. It could be 2, 4, 6, and you keep on going down until you get to 0. Let's look at example 2. Use Descartes' rule of signs to determine the possible number of positive and negative real zeros of each of the following polynomials. Okay? So right now our f of x, it's positive, positive, positive to negative. That's one change. And then that stays negative. So I think I misspoke earlier. It was that would have been 2. Positive, positive, negative, positive. Would have been 1 change, 2 change. This is just 1 change from positive to negative. So this is 1 change. So if we look at the number of positive zeros, negative zeros, and then we'd have complex zeros. So we could have 1 positive. So we're guaranteed that there's 1 positive. Not 2 or 3, there's 1 positive. So don't look, after you find 1 positive, don't keep looking on the positive side. That tells you when to stop looking. How about f of negative x? That's negative x cubed plus 2x squared minus negative x makes it plus 5x minus 6. So it goes from negative to positive, that's 1 change. And then positive to negative, that's another change. So there are 2 changes here. So we could have 1 positive, 2 negative, and 0 complex, or 1 positive, 0 negative, and 2 complex. Now, why 2 complex? Well, all the coefficients are real numbers. So that means if one of the roots is complex, its conjugate must be there as well. Because a complex number times its conjugate gives us a real number as a result. So it's either 1 positive, 2 negative, and no complex, 1 positive, 0 negative, and 2 complex. So this means if you do find 1 negative, there's 1 more negative there. Next one, positive, positive, positive. There are 0 sign changes. So we look at positive, negative, and complex. There are none here. G of negative x is negative x cubed plus 3x squared minus 3x plus 9. It goes from negative to positive, that's 1 change. Positive to negative, that's 1 change. Negative to positive, that's 1 change. That's 3 changes. So 3 negatives are possible. then 0 complex. And why do I stop there with 0? Because it's cubed, so we have 3 zeros. Some may be duplicates. Or 0 positive, 1 negative, you go down by 2, and 2 complex. Either way, I'm not going to look for any positives, I'm going to look negatives. Now, in this being a cubic, I'd find the first negative, and then I use the quadratic formula for the rest of it. Okay, I'm going to go on to the next page here. We're going to talk about upper and lower bounds of 0, of the zeros. This will tell us when to stop looking for bigger numbers. Assume f of x is a polynomial with real coefficients, again real, a positive leading coefficient and degree greater than or equal to 1. So positive leading coefficient, another key point here. Let a and b be fixed numbers with 0 between a and b. So it means a is less than b, a is less than 0, b is bigger than 0. Okay, so a less than 0, a is negative, b is positive. Then no real zero of f larger than b, we say b is an upper bound of the zeros of f if the last row in synthetic division of f of x by x minus b contains no negative numbers. That is, b is an upper bound of the zeros if the quotient and the remainder have no negative coefficients when f of x is divided by x minus b. So it would be an upper bound. Now, I typically look for my bounds within my list of potentials. The book doesn't always do that. So I just want to warn you on that. I would look in my list of values. No real zero of f is smaller than a, so we're talking on the negative side. We say a is a lower bound of the zeros of f if the last row in the synthetic division of f of x by x minus a has the entries that alternate in sign. 0 can be counted as either a positive or negative as necessary. Perform the following operations using g of x equals x cubed plus 3x squared plus 3x plus 9. So first thing, use synthetic division to identify the upper and lower bounds of the real zeros of the polynomials, and then find all the real zeros using polynomial division, quadratic formula, and so on. And the answers to part A. So, we saw this problem earlier, that g of x equals x cubed plus 3x squared plus 3x plus 9. This is from example 2b. We have positive, negative, and complex possibilities, potentials, and there was 0 positive, 3 negative, 0 complex is 0, 1, and 2. So with that in mind, I mean, if we look at our possible p's would be plus or minus, we're looking at factors of 9, 1, 3, and 9. Our q's would be plus or minus 1. So when we look at p over q, we're looking at just plus or minus 1, 3, and 9. So if I could just do division by the 1 in the box, we got 1, 3, 3, 9. We have 1, 1, 4, 4, 7, 7, 16. They're all positive, so I'd say 1 is an upper bound. I don't think we even needed to try that because I think we knew that there were no positive zeros of this. I hope we knew. Now let's look on the other side. What if we tried negative 3? Oh, look at that. So it goes from positive to not positive to positive, not positive. That would make this a lower bound because it said 0 can count as a positive or negative, whatever we need it to be. So positive, not positive, positive, not positive. So first of all, x equals negative 3 is a 0, and negative 3 is a lower bound. So I would not try 9. Don't even bother trying 9. You can try it, but it's not going to give you anything. Okay, so our upper bound is going to be 1. Lower bound is going to be -3. Now find all the real zeros using polynomial division. Well, from what we just saw here, we have x squared plus 3x. No, sorry, x squared plus 3 times x plus 3 from this. That's going to be equal to our x cubed plus 3x squared plus 3x plus 9. So if we take this x squared plus 3 equals 0, x squared equals 3, -3, x equals plus or minus the square root of -3, or x equals plus or minus I times the square root of 3. So the zeros are going to be -3, I times the square root of 3, and -I times the square root of 3. So this result is the second case, 1 negative and 2 complex. These are complex. We had 1 negative root and 2 complex. Okay, we're going to go on to the next page. I know this is a lot of stuff. This is things you haven't seen before, but we are learning new skills, pushing ourselves, finding zeros. Okay, the intermediate value theorem is a really cool theorem. That's the next concept, and you're going to see this in calculus too, a little bit different version of it. Well, a calculus version of it. But. Okay, here we go. Assume f of x is a polynomial, like here's our f of x, with real coefficients, and that a and b are real numbers, where a is less than b. If f of a and f of b differ in sign, then there's at least one point c such that c is between a and b where f of c is 0. So we're saying, like, okay, let's say here's our a, let's say here's our b. So down here is our f of a. Up here is our f of b. F of a is negative, f of b is positive. Sorry, f of a is negative, f of b is positive. So there's a place here c such that f of c equals 0. That is to say, your function is continuous. If you have a place, if you have it that for one value it's negative, the other value is positive, there must be a 0 in between. Likewise, this can be your a. This can be your b. There still must be a c between these, that f of c equals 0. So we're going to use this now, use the intermediate value theorem to show that the following polynomial has a real zero between the indicated values. So f of x is x to the fourth minus 9x squared minus 14, for x being 1 and 4. So f of 1 is going to be 1 to the fourth minus 9 times 1 squared minus 14. That's 1 minus 9 minus 14 equals -22. F of 4 is going to be 4 squared, 4 to the fourth, minus 9 times 4 squared, minus 14 equals, it's 256, minus 144, minus 14, that's 98. So that f of 1 was less than 0, f of 4 is greater than 0, so there must be a value c where 1's less than c less than 4 and f of c equals 0. That's kind of a cool theorem. We go on to the last page now. We're going to use any of the methods discussed in this section as guides and find all the real zeros of the following function. Hey, look, it's 3x to the 5th power. That means 5 zeros. Some could be duplicated. Have multiplicity too. So right off we have positive, 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 one sign change. So if we're looking at positives, negatives and complex. We could have one positive. So I would definitely look for that one positive. F of negative x is going to be negative 3x to the fifth plus 7x to the fourth minus 12x cubed plus 28x squared plus 15x minus 35. That's going to be one sign change, two sign changes. So negative to positive, positive, negative, negative to positive, three sign changes, four sign changes. So we could have four negatives and zero complex, one positive, two negatives and two complex, one positive, zero negatives and four complex. In the last case, I'd be really sad if that happens that way. So look for our P over Q's. Factors of 35, 1, 5, 7, and 35, plus or minus, and factors of 3, 1, and 3. So we're looking at plus or minus 1 over 1, 1 over 3, 5 over 1, 5 over 3, 7 over 1, 7 over 3, 35 over 1, 35 over 3, and sadly none of these are really going to reduce. 1, 2, 3, 4, 5, 6, 7, 8. We have 16 possibilities for them to be rational. Let's start with 5. We have negative 3, 7, negative 12, 28, 15, and negative 35. It's negative 15. Now, oh wait, it's positive. Positive 3. 7, positive 12, positive 28, negative 15, and negative 35. Okay, restarting. Because I couldn't use this. Well, I couldn't use the Descartes. Okay, we're good. It's 3, 15, 22. I could use Descartes. I couldn't use the other, the bound one, the limits. Okay, that's going to be 110. Ooh, this is getting big. 122. 5 times 122 is 244. Yeah, it's not right. It's 250. 122 times 5. 0, carry the 1. 5 times 2 is 10. That's 11. Carry the 1. 5 times 1 is 5. Plus 1 is 6. Okay, so it's 610. Then we're at 638. I think we see this is not going to go negative on us. And then we have 20 or 5 times 638. We have 3190. This is 3175. $15,875, and that's $15,840. All positive, so 5 is an upper bound. I'm not going to try a 7 or 35 or 35 thirds. Okay, erase this. Let's go to something smaller like 1. It's going to be 3, 10, 10, 22, 22, 50, 50, 35, 35, 0. Hey, so 1 is one of our zeros. Okay, cool. That's our single positive 0, so we're not going to try any more positive 0. So I'd say 1 is the, well, let's leave it like that. 1 is 0. Okay, let's continue then. What if we did negative 5? We have 3. I'm going to go with this row right here. 3, 7, 12, 28, no, 3, 10, 22, 50, and 35. 3, 15, negative 15, that's going to be negative 5. It's 25, that's going to be 47. Let's see, 47 times negative 5. It's going to be 35. 5 times 4 is 20. That's negative 235. 50 negative 235 would be negative 185. Negative times negative is a positive. 925. And we're at 960. So notice this goes positive, negative, positive, negative, positive. So that means that negative 5 is a lower bound. So let's try something bigger. How about negative 1? Negative 3, 7, negative 7, 15, negative 15, 35, negative 35, 0. Now these are all positive, so negative 1 is not a lower bound, but it is a 0. And look, now we have 4 terms to work with. Okay, sadly I think we're out of all our integers. 5, negative 1, so we have negative plus or minus 1/3, or negative 1/3, negative 5/3, and negative 7/3. So let's try negative 7/3. It's going to be negative 7, 0, 0, 15, negative 35, and 0. So we're left with 3x squared plus 15. That's what this is. So if we set that equal to 0, 3x squared equals negative 15. X squared is negative 5. X is plus or minus I times the square root of 5. So we have 1, negative 1, I root 5, negative I times the square root of 5. So all I do is I set the resulting quadratic equal to 0 and solve for it. So we end up with this situation right here. We had 1 positive, 2 negative, and 2 complex. And that'll do it for 4.3, locating real zeros of polynomials. I hope you enjoy this. I know it's going to be a little bit of work, but I believe you can do it. So good luck. Thank you, and send me your questions. Thanks.